My dear student, colleagues, and all the viewers who are watching this program live from Facebook page, Physics Center, and Astrophysics and Astronomy School YouTube channel, Pretam Kumar, I'd like to welcome you all to our International Physics webinar. Good evening to all here in Bangladesh, and a very good morning to all those who are watching this program live from USA and Canada. So hope you are well and safe from Corona pandemic. Today is a very important day and historic day for our department, as we are going to celebrate our 200th International Physics webinar with a Nobel laureate speaker. As we know that we are staying in a Corona pandemic situation, and we cannot continue our normal academic program inside the campus. We have to start our online program. I think you have already come to know that the Department of Physics, Pabna University of Science and Technology, has started its online program, including online international physics webinar. We have successfully completed our 199th international physics webinar, including 2 Nobel laureate speakers, and today it's our 3rd Nobel laureate speaker. So we are trying to adjust with this new normal situation, and the main aim of our program is to motivate and encourage our students in this Corona pandemic situation. Today, I'd like to welcome you all to a joint session between our department, Department of Physics, Pabna University of Science and Technology, and the Department of Physics and Astronomy, University of Waterloo, Canada. And we have with us here today Dr. Donna Strickland, Professor, Department of Physics and Astronomy, University of Waterloo, and Nobel laureate in Physics 2018. And she has already connected with us, so I'd like to welcome our speaker. So good morning, madam, and good evening here. So thanks for joining with us, and thanks for accepting our invitation. And we'd like to say thanks.
I would. Thank you very much. And this is my first time speaking for people in Bangladesh, so I appreciate this opportunity.
Great. We are very lucky, madam. And we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation. Before going to you, I'd like to introduce you, though anybody knows you. So I'd like to introduce you with our student and viewers. So dear student and viewers, I think you have already come to know that the title of this today's International Physics webinar, and title is the Generating High Intensity Ultrashort Optical Pulses, and our speaker is Dr. Donna Strickland, Professor, Department of Physics and Astronomy, University of Waterloo, Canada, Nobel laureate Physics 2018. So this is the abstract of our lecture. So we can see his bio. So Donna Strickland is a professor in the Department of Physics and Astronomy at the University of Waterloo, and is one of the recipients of the Nobel Prize in Physics 2018 for developing shift pulse amplification with Gerard Moreau, her PhD supervisor at that time. They published this Nobel-winning research in 1985 when Strickland was a PhD student at the University of Rochester in New York State. Together, they paved the way toward the most intense laser pulses ever created. The research has several publications today, application today in industry and medicine, including the cutting of the patient's corona in laser eye surgery, and machining small glasses parts for uses in cell phones. Donna Strickland was born in 1959 in Guelph in Canadian province of Ontario. Her mother was an English teacher and her father as electrical engineer. As a high school student, she excelled in math and physics, and only those, she says, some people are good at a lot of things. I don't know how they choose what to do. Strickland was a research associate at the National Research Council Canada, a physicist at Lawrence Livermore National Laboratory, and a member of technical staff at Princeton University. In 1997, she joined the University of Waterloo, where her ultrashort laser group develops high-intensity laser system for nonlinear optics investigations. She is a recipient of a Sloan Research Fellowship, a Premier Research Excellence Award, and a Cottrell Scholar Award. She served as the president of the Optical Society in 2013 and is a fellow of the OSA, Optical Society, and the Royal Society of Canada, and SPIE, International Society for Optics and Photonics. Strickland is an honorary fellow of the Canadian Academy of Engineering as well as the Institute of Physics. She received the Golden Plate Award from the Academy of Achievement and holds numerous honorary doctorates. In 1989, she got his PhD from the University of Rochester, and in 1981, she got his Bachelor of Engineering from the McMaster University. Donna Strickland thinks lasers are cool. With enthusiasm for the field and very hard work, she found a way to create high-intensity laser pulses. This technique, stripped pulse amplification, or CPA, was described the Strickland's very first scientific paper, and it led to her 2018 Nobel Prize in Physics. More important, it began a long career in which, as she has put it, this is his quote, "I get to pay with high-intensity lasers." And this is awards and distinction. In 2018, she got Nobel Prize, and 2008 Fellow of the Optical Society of America, 2000 Cottrell Scholar Awards from the Research Corporation, and 1999 Premier's Research Excellence Award, and 1998 Alfred P. Sloan Research Fellowship. Expertise: intense laser matter interaction, nonlinear optics, short pulse intense laser system. This is her research interest: ultra short pulse generation through multi-frequency Raman generation, two-color fiber laser system for mid-infrared generation, and self-focusing in the crystalline lens. And this is his publication list. Professional association and service. Google Scholar ID, you can see his Google Scholar citation number more than 10,000. So thanks for all your patience. Now it's time to go to our main speaker, our honorable speaker. So, madam, thanks again, and it's your time, madam. We are waiting for to listen to you, and it's your time. You can start your session.
Thank you very much, Dr. Das.
It's a pleasure, madam.
Just takes a minute.
It's okay.
Here we go. So that's it, right?
Yeah, we can see.
Okay. So thank you for having me and joining in this talk. This is my official title of the talk, and the unofficial title of the talk is, what did I do as a PhD student that got me the Nobel Prize? Or why was I the student in Gerard Mourou's group that got to do this Nobel Prize winning work? And it's really because I was the one in the group trying to do high intensity. So I'm going to walk us through, and the story is really about how every time scientists came up with new technology to make the intensity of light higher, it changed our understanding of how light and matter interact. So I'm going to go back before the laser and then walk us through until how CPA changed our understanding as well. So let's go all the way back to the 19th century. At this time, scientists were still trying to decide if light was a particle, made of particles, or made of waves, right? And there was reason to think both ways. And then along came a theorist, Maxwell, who really showed us that light had to be an electromagnetic wave. And pretty much all scientists looked at that and went, he's got to be right. It's got to be a wave. So now I'm only going to talk about the waves that we see with our eyes. And so we see light from red to violet, and the difference is the wavelength of the light, and that is the distance. Let me just see if I can get a pen here. So that's the distance between these two crests, is the wavelength. Red is the longest wavelength light that we see. We see green at our peak. That's the color we see easiest. And at the other edge, we see violet. We don't quite see what musicians would call an octave. So in sound frequencies, an octave is a factor of 2 difference in the wavelength or frequency. So this isn't quite a factor of 2 different. But anyway, these are the wavelengths that we see. So thinking about these wavelengths, scientists at the end of the 19th century said, all right, we have to prove that light's a wave, right? Even though the theorist says it must be, let's try to prove it. And we're going to do that with these experiments, which we're going to shine light on material and watch the electrons come off. In the same way, in a totally analogous way that you can walk along a beach. I hope you've all had a chance to walk along a beach, and in particular, a stony beach for this. But if you walk along a stony beach, you will see that the stones get pushed up the beach with the waves. But if the waves are very small, the stones barely move. And as the waves get bigger, the stones can get pushed quite a ways up the beach. And so we all have this sense that it is the height of the wave that brings the power, not the distance between the crests. So they decided they would use these different colors of light and then turn up the power and watch the speed of the electrons come off. When they used red light, no electrons came off. No matter how high they turned up the power, no electrons came off. When they used green light, electrons came off, but at very low speed. And when they turned up the power, more electrons came off, but still at low speed. And finally, with violet light, the electrons came off with higher speed. And again, when you turned up the power, more electrons came off, but always at that same speed. And so the speed went with the wavelength of the light and not the height of the amplitude. And this was very confusing. And so scientists were once again back going, what's going on here? How do we figure this out? And so it was this man, Albert Einstein, who solved so much of physics all on his own, apparently, could have won so many Nobel Prizes. But we in optics like to point out that what he did win the Nobel Prize for was explaining this, what's now called the photoelectric effect. He was the one who said the light field itself, the energy in the light field has to be quantized. And there is a minimum energy unit. And that's what we now call the photon. Okay. And so to understand the photon, though, it is a wave-like particle. And it was pointed out that it is the wavelength or the frequency of the light that gives the energy of the photon. And so red photons have different energy than violet photons. So now to understand the photoelectric effect, I'm going to use gravity instead, because I think we all understand the gravitational energy, that if you hold a ball higher up, it will be traveling faster when it hits the ground. And we change that gravitational potential energy into kinetic energy. So now let's imagine that what's going on is these photons are playing basketball with child-size basketball net, okay? I don't know how popular basketball is in Bangladesh, but I hope you understand the game. And it started in Canada. You might think it started in the United States, but it was a Canadian. Anyway, just saying. All right, so now the red photons are like child-sized photons. And even on their tippy toes, they cannot dunk their balls into the net. And this is why no electrons came off. So what is the power? What we're talking about is turning up the density of the photons, because the total energy is the energy of one photon multiplied by the total number of photons, and the power then is the rate these photons are coming. So it's more a density thing. So it would be more of these red child-sized photons all around the net, but none of them can reach the net. So no electrons came off. With your green photons, they're adult-sized photons playing with a child-sized net. And so they can easily dunk the ball and the ball goes through, but at this low speed. And again, if you turn up the power, what you're doing is surrounding the basketball net with all of these adult-sized photons, and they're all dropping their electrons through, but always at that same low speed. And finally, if you now have violet light, they're like the pro basketball players. They're the really tall ones. And so without even getting on their toes, they're well above this child-sized net. And when their balls go through, they have this high kinetic energy. And again, there would be more of them around the net if you turned up the power. So when we teach the photoelectric effect in our physics classes, it's usually about the quantum mechanics. But for this lecture, what I want us to concentrate on is the fact that the photoelectric effect is an example of a linear optical effect. It is a linear optical interaction with matter. And that is that it's always one photon interacting with one atom at a time. And if this photon has more energy than what the atom is holding on to its electron with, then the electron leaves with the difference in energy. Okay, so that's great. And then if we turn up the power, we have more photons at play meeting up with more atoms, releasing more electrons. But it's always one photon with one atom at a time. We call this a linear process, because then if you double the power, you double the number of electrons. Okay, so you double the electron power out, but not the power of the single electron. And again, if you added more, it would go linear. All right, so that's where we were with our understanding at the beginning of the 20th century. We understood that light and matter interacted in this linear way. And then along came this woman. Oops, can I get to this woman? There she is, Maria Goeppert-Mayer. Now, Maria Goeppert-Mayer is the second woman to win a Nobel Prize in physics, but not for this work. It was work she did at Argonne National Lab in the 50s on nuclear shell structure, which I'm not going to discuss at all. But when she was a graduate student in Germany, she asked the question, why can't atoms absorb the energy of two photons simultaneously? Why is it always one photon interact with one atom? Why can't two photons interact with one? Now, why she didn't win a Nobel Prize for this, I don't know, but it certainly started this whole new field of multiphoton physics, and I certainly referenced her PhD work in my own PhD work 30 years later, 50 years later, what am I saying? Okay, so what's the idea? Now, her actual paper is about two-photon absorption, leaving the atom in an excited state, but I want to stick with my idea of the photoelectric effect, because I ended up doing the multiphoton version of that for my thesis. So it's really just ionization. It's the idea that the electron is stripped from the atom. And so if you could simultaneously absorb the energy, they would add together. And if you had two red photons, it would look like an ultraviolet, because violet's not quite twice. And it would come out with this extra energy. All right. So she showed us that theoretically, this was absolutely possible. She went through the quantum mechanics and coupled that with Maxwell's equations. And she showed us that indeed, we should be able to see absorption of more than one photon at a time. 1931, she published this work, and nobody saw it until 1961. And it was Peter Franken's group at the University of Michigan that were the first to see it. Now, you'll see that I'm calling this a nonlinear optical interaction instead of a multiphoton. I will tell you it took me over 30 years to understand there was a difference. And the difference is really this, that if you are an atomic or molecular physicist and you watch what happens to the atom or the molecule, you're doing multiphoton physics. But if you watch what's happening to the light, then you're doing nonlinear optics. And so the first thing that was seen was a nonlinear optical interaction. So this group actually did witness the simultaneous absorption of two red photons. But rather than ionizing, that didn't happen. These had much stronger, they were holding onto the electrons more strongly. They also didn't see two photon absorption, which is a resonant effect. What they did see was that the atom momentarily absorbed the energy of the two red photons and released an ultraviolet photon. Okay. And so exactly twice the energy. And so this is a nonlinear optical effect because it changed the light that came out. Now, they only saw this happen in about 1 part in a million to 1 part in 10 million, but they did see it in 1961. So now that begs the question, why did it take 30 years after Maria Goeppert-Mayer told us it would happen for anybody to see it? And of course, the answer is the laser came along in 1960. So it was, again, as I pointed out at the beginning, a new technological development that helped us see a new type of light-matter interaction. So this is my Nobel talk, and so I do want to pay homage to all of the Nobel Prize winners that have gone ahead of me in this field. Basov and Prokhorov were working in Russia, while Towns was working in the United States, all on the maser. That is the microwave version of the laser, where L stands for light, M stood for microwave. That is the precursor and the one that was technologically easier to develop. And so that was done in the 50s. Art Shala won a Nobel Prize a few years later. He worked with Townsend and at Bell Labs, and together they really started to think about how to change the technology that would make a laser possible. Now, they're the ones that won the Nobel Prize, but it's really this man, Ted Maiman, who really demonstrated the laser for the very first time on May 16, 1960. All right, so he was the one who figured out how to do it. All right, now, what is it about the laser that made this nonlinear optics happen? Well, the light that's shining on me so that I'm lit up and you can see me through the camera is just your regular light bulb. It is white light, which is good for imaging. It's photons of every color. It's good for imaging because the photons go in every direction. But also, though, is that each photon isn't necessarily talking to any other photon. They're all doing their own thing. Now, usually when I'm giving this talk live, I use a laser pointer, and I can't see myself in this demonstration, so I hope I've got the camera in a good position here. But of course, as we all know, lasers go in a single direction, and they usually, certainly in this case, go with a single color, so that there's only the one color, they're going in the one direction, but most importantly, it is coherent. And that means the photons do know what each other are doing. And so they can all peak together and trough together. And so when this wave comes along, it becomes a giant wave or more intense wave, powerful wave. Intensity is power per unit area. All right, so now let's go back to the photon picture then of this high intensity to talk about why it helps with nonlinear optics. So again, if you go back to just regular light, the photons are, as I've pointed out, every color, which means they're each dancing to their own beat, okay? And they're each doing their own thing. And so I like to say they cannot crowd onto the dance floor very much. Now, what we need is if we're going to all get two photons simultaneously into this atom, we need huge density of photons. So in 3 dimensions, 2 dimensions is we use a lens and we focus down. And even though it looks like we're focusing to a point, we cannot, because of diffraction, focus any more than a wavelength of light. And so for visible light, it's about 1/2 a micron. Quite often the lasers are out at the 1 micron. And so we can only focus down to 1 micron, and we know that atoms are this like 10,000 times smaller. So if we blow up, the size of an atom and say, what is the chance of finding 2 photons in this interaction volume of the atom? It's just too small to see. And that's why before the laser was invented, nobody actually saw it happen. And then when the laser came along, now we have all the photons dancing together. Now, before I describe this, let me say that Nicholas Bloomberg won the Nobel Prize with Art Shallow for laser spectroscopy, but I leave his picture with this one because he is sort of considered the father of nonlinear optics, where I guess Maria Goeppert-Mayer would be the mother of multiphoton physics. So, okay, so now we have the laser light. They're all dancing, to the same beat, and they're all dancing together so they can crowd in on this dance floor. And so because the density of photons can be much higher, that's the same thing as saying that the classical wave has gotten a bigger amplitude, but it's almost the same thing. There is some possibility in this interaction volume of the atom that you will find more than 1 photon in that volume. I also think Maria Goeppert-Mayer, for those of you that are physicists, studied 2-photon absorption because that is a resonant process. The 3rd dimension here is the interaction time, the length though with speed of light, that gives you a length. And so it would have the biggest interaction volume. But it was also seen in 1961, but it was the non-resonant process of harmonic generation that was seen first in a much smaller volume. But again, it was 1 part in a million to 1 part in 10 million. Okay, so very small chance, but there was that chance when the laser came along of finding 2 photons in this volume. So what has any of this got to do with me and my PhD? When I first joined George's group, he gave me this paper written by Stephen Harris, a professor at Stanford University. And Stephen's paper was a theoretical paper, but it was about, okay, great, we now have lasers. It was 1973. We have lasers. They're mostly in the infrared and then into the red region. I'm trying to remember if there might have been some more visible than just red. But we were there, and we had coherent light now, and we could do 2nd and maybe even 3rd harmonic generation. But he's going, how do we get it out? How do we get this coherent radiation further out into the XUV and possibly even X-rays? And so he thought, no, let's do high order harmonic generation. And so to do it, he was going to exploit resonances. Okay, and I'm not going to get into that in this talk. But anyway, he came up with this way, and he had even versions of how to do the 15th harmonic. Gerard asked me to look at the paper and see if with the lasers we had, could we come up with something? And I came up with the fact that we could exploit an 8th photon resonance of twice ionized nickel to make the 9th harmonic. So that was going to be my PhD. I was going to try to make the 9th order harmonic of a neodymium YAG laser using twice ionized nickel. I never did make a cold plasma of twice ionized nickel, never did that experiment for my PhD. But it required me first to try to figure out how to make that cold plasma of twice ionized nickel. And also, I didn't just need 2 or 3 photons in that interaction volume. I was going to need 9 photons in that interaction volume. And so I was not going to just need a laser. I was going to need a really intense laser. So that was the other part of my project, and that's really the part that was successful, and that's what we're going to discuss. All right, so how do we get an intense laser beam? So even though I've been working with lasers for 40 years now, I'm still amazed at how fast light travels. So if I take my, is it still on? Let me see. If I take my laser beam that I have here, and I'm sitting beside my dining room window, I could shine it out. And if the moon was out in that direction, which I doubt it is, and I made a 1-second light pulse, right? So I start here, I put my finger across, I open up for 1 second and shut it off. If I did that and shone it towards the moon, it travels more than 2/3 of the way to the moon before I've shut the pulse off. I mean, that's so amazing to me. 1 second and you can get 2/3 of the way to the moon if you're light, okay? If I was trying to fly to Bangladesh to give this talk, it takes a better part of a day for me to get there, but light can get there in no time. So a 1 second light pulse is 300,000 kilometers long. Now you'll see I've got the energy here of 1 millijoule. So why 1 millijoule? Well, this is about a 1 milliwatt laser in order to be eye safe, okay? And so power is energy per unit time. So every second, this 1 milliwatt of power comes out, means there's 1 millijoule of energy coming out. So if I made that 1 second light pulse, it would have 1 millijoule energy in it. Now, I was shining it on my hand and I can barely feel it. I have to hold it very stable for it to start even feeling it getting warm. So 1 millijoule doesn't seem like that's very much energy. And yet I will tell you that first, it was all the energy I had in that very first laser that I published in 1985, won me a Nobel Prize. Enough for that. But also, that's all it takes to do the corneal surgery that I will show at the end of this talk. It's all it takes to cut the glass. And yet, I'm having 1 millijoule land on my hand every second, and it doesn't even hurt. And so what's the difference? The difference is the intensity. It's not just the energy, okay? Now, sometimes it is the energy. Laser fusion is an example. But sometimes, just like driving a nail into a piece of wood where you would push with all your might and nothing happens, but you pick up a hammer and do it quickly, the nail goes in. I like to say that I built a laser hammer. And so we're going to try to squeeze all the energy that's over 300,000 kilometers. I usually have my hands way out, but won't be on the camera here. And squeeze it down. So let's go to the first nonlinear optics experiment done in Michigan. They had a millisecond pulse, still 300 kilometers long. I will also say they used 1 joule. So they had 1 million times more power in their beam than this does, in order to see that 1 in a million to 1 in 10 million, all right? So that's obviously not enough for me to get 9 photons. And so what we were talking about was squeezing all that energy down. The 1 millijoule of energy in this that stretches over 300,000 kilometers is now squeezed down to 0.3 millimeters, all right? Then, of course, we use a lens to squeeze it down in the other 2 dimensions, but we can squeeze it in time down to 0.3 millimeters in length. All right, so that's what we're going to talk about. The question is, how did we do it? So let's go back to Earth, and we're going to go to Rochester, New York, where I was a graduate student at the University of Rochester, and I did the research at the Laboratory for Laser Energetics, which is a Department of Energy lab studying laser fusion. And that's a picture of me as a young grad student. And I believe my father took this picture because that's his car. All right, so now let's go into this lab. This was the very first lab I saw in George's group. It's a dye laser. It is a red laser pumped by this green beam. The dye just comes through this hose right here. If it did spill on your clothes were dyed red, or sort of orangey red. Okay, so this was already an example in Gerard's group when I joined of 100 femtosecond pulses. That's 10 times shorter. That says the pulses are only 1/30 of a millimeter long. Okay, these are very tiny pancakes of light flying through the air. So we already had short pulses, but a dye laser cannot get to be a high energy laser. And I'm going to explain that later in the talk. So we had very short pulses. Now, right across the lobby was this big laser, the Omega laser. This is the laser that was used for fusion. Fusion is an application that requires energy. This laser is a kilojoule. So it is 1,000,000 times more energetic than what I'm talking about when I talk about the millijoule laser, or what the dye laser can do, which is a millijoule. Now, just to know, this is almost like a football-sized field. This object here is about the size of an adult. Okay, so this is a big laser. And in order to get big energy, you need a big laser. Again, I'll explain that later in the talk. These beams here, these are frequency tripled to ultraviolet, and it's strong enough to be ionizing the air. So that's what you're seeing here, is in this picture, the air is being ionized. So we had big energy lasers and we had short pulse lasers, but we could not put the short pulse into the big energy. And that's why we needed CPA. So this is George and my Nobel picture now, and this is us having a ball at the Nobel Ball on December 10th, 2018. So, like I said, I like to say that we want to build a laser hammer. That means we have a lot of energy in a short pulse. The reason that you cannot directly amplify your short pulses in an amplifier is that you would have that laser hammer inside the amplifier. And when people first put short pulses down these big energy systems, they saw very quickly that they drilled damaged spots right along the laser line, right? And that's why they stopped doing it. And they also then, when other people went off to study, why was it happening? What nonlinear optical process was happening to cause this damage? And it is self-focusing. So anyway, so this is why we needed chirped pulse amplification. We wanted a laser hammer. We don't want it in the amplifier. So it's a very simple Nobel Physics Prize to understand. This is all it is. We want to amplify this short pulse to big energy. To do it, we can only have long pulses go through, so we stretch the pulses and make them long. Once it's very long, so that the peak power cannot get high in the amplifier, we go ahead and amplify it to the total energy. And remember, power is energy per unit time. So we're keeping the peak power down, because nonlinear optics goes with power or photon density. Once it's all the energy that we want out of the system, then we can compress it back to a short pulse. In our day, we did it in air, but now with the biggest systems out there, the compressor sits inside vacuum, because even air becomes a nonlinear medium with the highest intensity pulses that we have now. So that's the very simple idea. We, of course, could call it stretched pulse amplification. We chose to call this chirped pulse. A chirp, a bird's chirp, or this type of chirp, just means the frequency changes in time through the pulse, okay? And so we use the dispersion, as I'll explain, to have the red colors out ahead of the blue colors. And so we had a chirped pulse. So how did we do it? Now I'm back in the same lab, although now I'm calling it neodymium YAG laser rather than dye. So we didn't use this laser. We used the pump laser, which is the one back here. This is a neodymium YAG laser. It puts out pulses that are about 150 picoseconds long. So it's short, but not too short. It wasn't really short enough, but anyway, 150 picoseconds. It lasers in the infrared. So this is why the camera can't see it. You can't see it with your eye. This is a frequency doubling crystal. So this is the same process that the Franken group saw in 1961. But now the intensities are high enough that we have 10% frequency conversion. Not 1 part in a million, but 10%. All right, so this was a 2-watt system. We had a 200 milliwatt green beam coming around here, but most of the energy is still in the infrared. These laser mirrors are very good at reflecting the color they want to reflect, but the rest, the infrared went right through and into a beam dump here. This is the light that we're going to use for the system. You'll notice that it's a very crowded lab. There I am in 1984. The laser that I showed you was coming this way. Okay, and so instead of the beam dump, we now have a fiber coupler here. There's my fiber. This is the output for the time. So this is 1984. Eventually, once we got the light coming through, this fiber was then put through the air duct to go to another lab at the other end of the laser lab, because there was simply no room left in this lab for me to build the amplifier. I like to point out that this is the cover of the quarterly review for LLE. They always had a student on the cover. It was my turn. They showed that we're laser safe, so I have to have my goggles on, but it needed green glass to stop the infrared, and the photographer didn't like the green glass in front of my eyes, so actually I'm only wearing frames here. But it doesn't matter, since it's an infrared laser. You couldn't tell if it's on or off, so it's just off. Okay, so now, why does it first have to go into a fiber? There's several reasons. One I can't explain to you in this talk is that the 150 picoseconds was too long. So we are going to use a nonlinear optics effect inside the fiber that creates more bandwidth to make a shorter pulse. I will talk about why we need a lot of bandwidth to make a shorter pulse. Once we have all of those colors, then it's this fiber that we use the dispersion. The fact that different colors travel different speeds in glass caused the dispersion that we need. All right, so first I said we need a lot of color to make a short pulse. Now, when we talk about this type of laser, and usually when we start talking about lasers, we talk about how it's just a single color. But it doesn't have to be. You can have a gain medium that would allow many colors to laze at the same time. And if you look at this picture then, and we just use the same colors that we see, and we say we have to have a certain point in space and time where they're all going to peak. We use a device in the laser called a mode locker. It is like a conductor of an orchestra. And so when you hear the orchestra just warming up, they're all playing their own notes, whenever they feel like it, it makes not pretty music. But when the conductor brings down the baton and they all play their different notes together, we get beautiful music. So that's what a mode locker does. It says, go now. So every color goes now. So every color is at a peak. And so they add constructively to be a giant peak. This is, all staying at 1 here, but this would be a giant peak. They've come apart a little bit here, so the troughs won't be quite as low as the peak is high. But you can see as we travel away from this peak, the different colors, are spread out. And by the time you get out here, there's as much peak as there is trough. And so they add up to 0. And so this is how we make a short pulse. This is the black is the pulse. This is what's known as a Fourier transform limited pulse, and that the spacing of the crests is constant. So it looks like there's only one color there. But the fact that it's a short pulse tells you that all those colors have to be there. And it's as important to add constructively as it is destructively in order to make that short pulse. So we need a lot of color. Once we have that color, then we're going to use what I call this dispersion. So what does dispersion come from? So at the beginning of my talk, I talked about ionizing because the photon would have more than the energy being held, the electrons being held by the atom. But the atom's energies are quantized. There are different levels here that we can speak at. If you have a glass, which is clear, that tells you that the lowest energy levels are actually up in the ultraviolet. So the photon comes along and tries to say, do I have anything in common with this atom? And, it's way down here and the energy's up here. And they go, no, not much in common. No point hanging around to talk. The green starts to get closer, but still not much. And the blue starts to get there. Now, it's not going to absorb. Otherwise, it would stay and be absorbed. We don't want that. It's clear, so it's not going to. But it travels slower because it takes a little bit longer to decide if it has something in common or not. And so as the light goes down this 1.4 kilometers of fiber, the red photons are running, the green are walking, and the blue are sort of crawling along. And so by the end of my 1.4 kilometers of fiber, I have stretched the pulse to 350 picoseconds. I would like it to be a nanosecond, but this is all we had, 1.4 kilometers. It was long enough to get the project done. All right, so the next step, once we have the stretched pulse, is to do the laser amplification. So we have these atoms here. We have to put energy in. And so again, this is the idea that there are these energy levels in an atom. We've taken it from the ground state. The pump has put it up into this upper state. And then the dye laser, I said, is not a good high energy system. And that's because it's actually a very good gain medium. It wants to get rid of its energy. So it doesn't stay around waiting for another photon to come along. This would de-excite and cause a photon to go in some direction. If it went in this direction, it could get gain and go out this way, it could go out this way, it could go in all directions, and you would lose the energy that's stored right now. On the other hand, glass, which is the type used for fusion, neodymium glass system, it can hang on to that light for quite some time and wait for a photon to come along. Now, I do like to point out to my atomic and molecular physics friends when they're in the audience that I'm an optics person. So in my pictures, the atoms have no personality, and you can tell the photons because they're the ones with the personality. But they are the very same color. This photon energy is the same energy that the atom is excited to. And so the photon, instead of absorbing, it's in the excited state. This is what Einstein let us know, because he's even the beginning of lasers, said that stimulated emission would happen equally to absorption. It's just that you start at the upper state. So this photon comes along and meets this atom and says, hey, I'll take your energy and we'll walk hand in hand. We're going to go in this coherent way and know exactly what each other's doing. Those two photons will meet two more atoms and become 4, and the 4 will become 8. So this is this exponential growth that all lasing starts with. All lasing starts with that one noise photon and takes off. But if you stay in this exponential region of gain, you will find that most of the energy was left behind. Okay. And so this is one of the reasons that we have mirrors that make up a cavity to make the beam go back and forth and back and forth. And you don't take the energy out until you go in with what's known as the saturation flux. And it's like a snowplow coming through and taking all the energy. Now, if you want to get more energy, then you have to go make the beam bigger and go back to the same energy per unit area to an amplifier. You go in with that snowplow, take out the energy. At the end, you have to make the beam bigger so that you go back in with that same energy per unit area to the next amplifier and take out the energy. This is why the big energy systems are big lasers, okay? To get that kilojoule. Glass works at, the saturation flux is 5 joules per square centimeter. So that tells you for a kilojoule beam how big the beam must be in order to get out that energy. So you want to run every laser system and pulling out this energy at this energy flux. So that determines the energy per unit area. Every gain medium has its level of nonlinearity. And so that says that you have to keep the photon density below a certain amount so you don't have this nonlinear optics problem happening where it was causing damage. So for the neodymium glass, it was about a terawatt of peak power, okay? And so that determines the density of the photons. That determines how long the pulse has to be in order to be able to get all the energy out of the system. And so for glass, the 5 joules per square centimeter said you really should have a nanosecond long pulse. And finally, now it's time to compress. And so we have our red photons out ahead of our green and our blue. We're going to use 2 parallel gratings. Gratings act like prisms. They actually refract or diffract the different colors to different angles. And if you watch the red now, the red actually off of 2 parallel gratings. After the parallel gratings, all the beams will be traveling at the same angle. The red has now had to travel further so that the blue can catch up to the red. And so that's how we do the compression and put all the colors back together and make a short pulse. So this was the measurement that showed it work. I had no way to measure, and it was my colleague Steve Williamson who had what's known as a Streaky Camera. It was a way to measure high energy pulses and single shot pulses and how short they were. And so this was the one that showed that it was at the best. We actually were limited by the camera to 2 picoseconds. But when I did the pulse compression at low power, I already knew from my own measurement that it was no better than 1.5 picoseconds. So we knew that the amplification did not destroy the phases and that we were able to compress. And so that's it. So that's the laser. So let's go back to the beginning of the talk when I talked about the linear photoelectric effect. And so by the time I got the laser to work, and we actually had the joule system, not just the millijoule, in this 2 picoseconds, I still did not have twice ionized nickel. On top of that, somebody had seen the 31st harmonic, so why would I even be looking for the 9th harmonic? And Si Long Chin had come down to do a sabbatical with Girard, and he wanted to be one of the first people to use this new CPA laser. And he convinced Girard that I should just do multiphoton ionization, that I had a high intensity laser that nobody else had, and I could see new things. So we were going to see, was I going to see multiphoton ionization? And so this is the idea that it would be an 11 photon effect and kick the electron out of its well, okay? So if that was going to be the case, it would have gone with the 11th power, and that's not what we saw. So now we had so much intensity, we didn't really have to think about the photon picture anymore. We actually were back to just a big, giant classical wave. And that classical wave came and sort of tipped the potential energy of the atom over so that the electron was free to leave. And so again, with new laser technology and with chirp pulse amplification, we had a new understanding of how light and matter could interact at these very high intensities. And so then it had to change our understanding of how that worked. And that's what led to some new applications. So this is something I've gotten from Girard, who's shown this picture over the years. When the laser came along in 1960, we had this high intensity. Q switching and mode locking were the ways to make the pulses shorter. It happened very quickly. But as I said, we could not put the short pulses into the big energy systems. And that's why the focused intensity did not change through the 70s. CPA came along in 1985. It took 10 years for Lawrence Livermore National Lab to figure out how to do it with their kilojoule laser systems and to have a kilojoule in a picosecond making a petawatt. And the real issue was the gratings. When I said I had a joule in my system, we couldn't actually put the full joule on the gratings that we had. They would have damaged. And so they had to figure out the damage threshold, I think, was like 20 to 50 millijoules per square centimeter. And they get very expensive for the gratings as they get big. So Livermore figured out how to make high efficiency gratings that were very perfectly grooved in order to have the compression work right and still have 1 joule per square centimeter damage threshold and make them over 1 meter big. This is Girard's laser at Michigan. It's actually not as powerful as this one, but they showed with deformable mirrors that they could actually focus right down to single wavelength dimensions. And so they got to 10 to the 21. I will say that a group in Korea now has a 4 petawatt system, and they just announced, I think a month or so ago, I've lost track of time, that they got to 10 to the 23 watts per square centimeter. So I don't know if that's really 2 orders of magnitude, but I already had the dotted line, okay? This one is blue. This is the 10 petawatt system that has been announced since COVID anyway, but longer ago. They have not actually done the measurement yet of focused intensity. So it could be there. It could be a couple, factor of 2 higher than this one because it's 10 petawatts and this is 4. When Girard started showing us this, though, he thought we would be up here by now because he just drew a straight line. This is nonlinear QED. This is where at 10 to the 29 watts per square centimeter, then if you take the energy of an electron and the energy of a positron, the rest energy, over that distance of the Compton wavelength. So this is what is vacuum? Well, we think it's this matter and antimatter held together. So they are dipoles, an electron and a positron, over this very small distance. And so the force of that energy, over that length is the same as the force that would happen at the focus at 10 to the 29 watts per square centimeter. So we should see matter come out of vacuum at that point. I've redrawn his line to show that it is curving over, and to really be honest, I should go back and get the people that made this for me to curve it over a bit more. All right, so I do like to point out to the students, it's time for a new Nobel Prize winning idea to get us another kick up there, okay? But let's talk about just back here with this new understanding of light matter interactions, how did the applications that we're talking about are down here. So laser machining is quite often done with CW lasers. There's beautiful YouTube videos of kilowatt fiber lasers drilling steel. But that's still a thermal process. The steel is basically black to the light. The light gets absorbed and it's heated up to melt or evaporate away. And so then that heat gets dissipated through the whole material until you can't cut very fine holes. Nanoseconds a little bit better, but what we're talking about is a laser hammer. So we're not even talking about using absorption at all, although this still shows it as black. But now we don't need to absorb it. We also want to remember that if you use lenses to focus down tight, that at the surface, the density could still be quite small and not cause any damage to the surface. But at the focus, it would start to ionize. And if we're talking about now objects like the cornea of the eye or the glass, right, the light will go through, it's transparent, and nothing's going to hurt the edge. So now we can machine inside transparent objects for the first time, because it's only at the focus where the intensity is high enough to cause that hammering and cause that electron to go right off the atom. So now if you're squeamish, please don't watch this video, but this is the eye surgery that was made possible. It was about 10 years after the CPA came along. And again, what it's going to do is cut the flap. It does not reshape the eye yet. That's still using excimer lasers, but your nerves are on the outside of your eye. And so you don't want to shape the original shape, the outside of your cornea, but that was very painful to recover from. So now they go ahead and cut this flap. And so the laser is being raster scanned back and forth over 17 seconds. And again, it's a damage down below. So this is the part that I find trouble watching. The surgeon's going to come in here with tweezers now and lift the flap just to show you that indeed it was damaged, that raster scan of damage through there, and left a cut underneath the cornea. And so the tweezers will come along here now and show that it's just a flap. There it is. Okay? I'm not going to show you the rest. That's it for the science I'm going to talk about. I have just a few minutes left. I'm just going to talk a little bit about Nobel Week because most of us do not get to see this. You know, some places in the world it's televised, but a lot of places it's not. It is a very special ceremony, and it's held in this concert hall. The royal family is sitting here on the stage with us. This is the King of Sweden, his wife, the Queen, the firstborn child, the Crown Princess, and her husband. The people in the red chairs is the current crop of Nobel laureates. The people that sit behind us are previous Nobel laureates. The people over here are the members of the Royal Swedish Academies that have chosen us. I will say that our families sit up here. So this is my husband, my sister, my brother, my daughter, and my son. And so we can see them very clearly while we're sitting on the stage. All the family members are sitting here. The rest of our guests are sitting elsewhere that I could not ever find. I kept looking for them, but then I kept thinking, oh, I'm going to look funny on camera if I keep craning my neck looking for them. We go early in the day to practice standing here to get the prize from the king and how to take it from his hand. Let me say something about that later. So there we are. Gerard and I are standing for ours. In physics, we are proud to say that Nobel recognized physics in his will first, and so the physics prize always goes first. I had been hoping to go back this year. I got invited to go back, and so I was hoping to be one of these people. And when I look at this picture, I always point out these two gentlemen that don't look too happy that CPA won, to remember to keep a smile on my face because you never know when the cameras are on you. And that's me. I've gotten my medal from the king's hand. And so what you practice actually is the fact that when the king gives it to you, it will be in the center of the diploma. You get a beautiful piece of artwork that's just for you and your certificate that's just for you. The medal actually has your name on it as well. He then uses his thumb to slide it under your thumb so that you can let go of this hand, he lets go of that hand, and we shake hands. That's what we rehearse. We also rehearse bowing to the king, then bowing to the Swedish Academies, and then finally bowing to the audience. So I'm very happy here because I've gotten through all of this process and I have not dropped the medal. And this is me receiving the prize. After the ceremony, you then go off to the banquet. So you are given this invitation. Here's Gerard's holding his. This is my husband holding his. Mine's, I think, already in my clutch bag. But you're given two numbers with your invitation. I was given the number 2 and the number 1. My husband was given the number 2 and the number 14. So here we are lining up for the first number, and Gerard and his wife was given the number 1. Again, physics comes first. And we also then go alphabetical, but Art Ashkin should have, and his wife should have been here, but unfortunately Art was ill and could not attend the ceremonies. His son came in his place, but because he was not a Nobel laureate, he had to go back into 10th spot. I also will point out that all French women that come get dressed by French designers, and Marcel Amou was dressed by Dior. She was also given jewels to wear. And this is because it is a red carpet ceremony and it is shown in France. And so they're willing to design. Canada, it's not shown on TV, so no designers came forward. I had to go to a department store and buy my own gown. We did not realize we'd both be wearing red. Anyways, after physics comes chemistry, and then we go down. So what are we doing here? We are in this room. The first time I gave this talk, I called it the gold room. And my sister was in the audience, and later she corrected me. She said, that's not the gold room. So can you imagine, this is the city hall in Stockholm. This is not the palace, this is City Hall, and there's an even more golden room just perpendicular to this one. But what we're doing is everybody that's going to be sitting at the center table at the banquet is lined up here, and we are waiting to meet the royal family. The royal family will come through this door and come and greet all of us. After they have greeted us, these people with the white hats are going to come and get us and take us to our second number. So my husband would be ushered to stand here, where I was ushered to stand at number 1. So why am I a number 1? As I've already said, physics is first. But by Swedish royal protocol, you must sit boy, girl, boy, girl. And so I was the one that got to walk in with the king. So there it is. I'm very excited to be walking into the banquet on the arm of the King of Sweden. And I will say that there I am, just having the time of my life, sitting with the King of Sweden. Now, there was just a whole bank of photographers on the other side. He was obviously watching one. I was watching another one. But when the cameras weren't there, we just had a delightful conversation through the banquet. The next day, all your 14 guests go home, but you and your partner get invited to the palace. So this is the dining room of the palace of the royal family in Stockholm. This time I sat beside his son, not the crown prince, but the prince. And he really was, to me, just Prince Charming. I really enjoyed sitting there in this incredible, incredible room. So I do like to point out that I somehow just went from being a grad student trying to do a really good PhD thesis to landing in a fairy tale. I just felt like I was definitely right in the middle of a fairy tale this night. And then finally on December 12th, which is the end of Nobel week, it starts on November 6th, you were brought, this is when you get back. So they do take away your medal and everything before the banquet, and they put it out on display in the ballroom where people are dancing because you don't want to have to lug this around the whole evening anyway. So they give it back to you on the 12th along with the money that goes with the prize. But the last thing they ask you to do really is sign this register. And then before you sign it, they show you some of the signatures. And I think for all physicists, they start with Albert Einstein's signature. And for me, they showed me Marie Curie's signature and Maria Goeppels-Mayer's signature. You then get to look through the book, but that's me signing my name. It is the most surreal moment of my life. I couldn't believe I was signing the same book as those incredible legends of the field. It was a tremendous moment for me. Anyway, I think that's the end of my talk. So I will thank all these people. Obviously, these are the people that helped me with the first CPA. Steve, as I said, helped take the data. Marcel Bouvier was our electronics engineer, and he just kept that really old laser I had working. These, I said, Silong Chin came and said, let's do multiphoton ionization. These are the people that help with that. And these are the people that helped me make this presentation. Thank you very much.
Thank you, Mera, for your wonderful and exciting presentation. And I think students and viewers have learned a lot of things, and they have enjoyed it. So we have got a lot of questions in comment section. If you allow, we can start our discussion session.
Yes.
So I'll start. First question we can take from comment. So how ultrafast optical pulses are used in steering high energy electron beams in plasma accelerator?
Oh, okay. Yes. Yeah, I used to have pictures of that. So it is called Wakefield acceleration. It is the same idea as in a boat in water, you will see the wave behind it traveling behind the boat. And so the idea is that when the laser pulse goes through this high intensity, there's something called a ponderomotive force. And that's the fact that if you can imagine, the energy is much higher in the center of the pulse. And so it's wiggling the electrons a whole lot more than the outside, where the intensity is less. And so that kinetic energy is sort of the same as a potential energy. And so it's sort of like this potential energy hill going through the plasma and making the electrons come out. And so that's what leaves the wake behind. And so now you have this plasma wave where the electrons are separated from their ions, and it's a wave traveling. And so now you have this huge electric field of the plasma wave between the electrons and the ions traveling. And so that's how it gets accelerated. I don't study the field myself, so that's as much as I'm going to explain.
Thank you. So we have another question. So how ultra-fast laser pulses are useful in neutron imaging?
I'm sorry, I didn't know they were used in neutron imaging, so I'm sorry, I can't answer that. If they're used in neutron imaging, that's a new one to me.
We can go another question. So how the mechanism of geometric optical object pulse temporal reconstruction relates to the known method of time resolved holography?
Oh, well, you're still going out of my field, because that's not high intensity either. I think, it is just the fact that there is time dependence there.
Okay, madam, we can go another question. So can we use second time scale light pulses emitted from the quark blown plasma in the study of ultra-fast process of nature, like the process happening inside the atomic nuclei?
Okay, so this goes along with the idea of why are we being limited right now in the intensity that we can get with CPA, and it's really because of the wavelengths that we're talking about. And so we've gone on to do high order harmonic generation and gotten to attoseconds, right? So in order to get to attoseconds and the pulses, the period of the light has to be shorter than what you're trying to get to, right? So visible light has periods on the order of 1 to 2 femtoseconds, so you shouldn't get pulses shorter than that. If you can get out to the VUV with these harmonics, you can get to attoseconds. If you want to go even shorter than that, you have to keep going up into the various other regions. So I've never heard of yoptoseconds either, but we will have to go further into the X-rays and all the way up towards gamma rays in order to keep going shorter and shorter. So yes, it can help, but on the other hand, if you're going to use them from the technique you talked about, you would have to be able to gather those photons and be able to detect those photons. And so you need a lot more technology all around in order to do pump probe at those very short wavelengths in order to see these things.
Yeah, thank you, madam. We have another question. To operate an optical quiz, what wavelength of the light is needed, and how to make sure that the focal plane of the beam and the laser are the same?
Okay, again, that was Art Ashkin's Nobel Prize, not mine. So I'm not an optical tweezers person, but it has nothing to do with, that one has nothing to do with the wavelength. That really has to do with how tightly you focus it and the gradient of that causing the force back in.
Okay, we have another question. So according to the result of Einstein Photoelectric Effect experiment, the question is, there is a threshold wavelength. At longer wavelengths, photoelectrons are produced, while at shorter wavelengths, they are not. So why? Answer this question, madam.
No, it's the other way around. The long wavelengths, they're not produced. This is what I tried to explain with the basketball. The long wavelengths are the low energy photons. And so the atoms are being held at higher energies. And so it just depends on which kind of material you're doing. If you're doing metal, which looks black to us, that tells you it does absorb light in the visible. And so it's, green, blue light probably can cause electrons to come off. Whereas transparent, you have to be in the ultraviolet in order for electrons to come off. But the photon energy has to be greater than the ionization energy of whatever atom you're talking about.
Okay, madam, thank you. We have another question. So how did you become interested in science, especially in physics?
Well, I think that you already said that in your opening remarks. I really, didn't have much choice. I was not athletic. I was not artistic. I didn't enjoy writing. So I was good at math, and I enjoyed. To me, math was just like doing puzzles. I like doing puzzles, and same with physics. It's just sort of a math puzzle with an actual application to it or something, right? So that to me was just, and it was also what I was very good at. And so I really had no choice. It was pretty much said to me, this is what you're supposed to do, so go do it. So that's why.
Thank you. We have another question. So do the photons have mass?
Not that I've ever heard of. So if you've learned new research, I would say no.
We have another question. Can you use pulse composition in optical fiber?
Do they mean pulse compression? I think they must mean pulse compression in optical fiber. That is the beginning. Actually, the year, like in 1984, when I give my physics version of this talk, I talk about how we went to the Ultrafast conference and the CLEO, which is the big laser conference, and people were doing fiber optic pulse compression. So as I said, the neodymium YAG laser was 150 picoseconds. So we actually did have to do fiber pulse compression in order to get the down to a picosecond type pulse duration. And so that is self-phase modulation happening inside the fiber, right? And so that causes the extra colors to show up. And then once you have the extra colors, but it was also what they showed in 1984 was that in order to not, self-phase modulation gives you this weird S shape of color and you couldn't compress it. But if you actually use a long enough fiber and had dispersion happening at the same time as the self-phase modulation, you got this nice linear chirp, which you could compress. And so it was right after that the light bulb went off and went, that's how we do CPA. You already have stretched pulses. We just need to put the amplifier before the compressor and we're done.
So thank you. This may be the last question. So, okay. So once you said that your beloved mother loved mathematics and you are an inspiration of many Indians, village girl like me. Please share some childhood memories. Thank you.
Well, yeah. So my mother, she came from a very small farming village. Her dad was a farmer, and the brother took over the farm, and yet both girls in the family did go to university from the small village in the 1940s. It was very rare, but they were both, and they were very proud of it. They were both the top student in their little high schools, and so they knew they were meant to go on to university, and the father was supportive of that, and so they went to university. Now, the sister went sooner, and she went into nursing. And she just said, don't, I think it was her sister maybe convinced her that science was too male oriented and she, it wouldn't work for her. She should really go to the art side of campus. And so she did. And then I grew up hearing her, just go on and on and on. Don't ever let anybody tell you what you're good at or what you should do. Pick yourself, so she was disappointed with that. I'll also say that I heard stories about my dad's family. My dad's father came from a fishing village in Newfoundland and had no schooling whatsoever. There was no school when he was growing up in the 1880s. And so he came over to Nova Scotia and he could not read or write. And he didn't learn to read or write until he retired. And then it was my dad's cousin's husband that, had time to teach him to read and write as an elderly person. And so I think my dad grew up knowing how important education was, when he was growing up in the 30s. And his brother was so smart, supposedly, that they didn't even have the final year of high school in this small town in Eastern Canada at the time. And the teacher said, oh, this is a shame. I'm going to teach you correspondence. You're going to take the final year of high school by correspondence, and I'll be your teacher. And the banker's wife said, I will help pay for your education, or I'll loan you the money. And the town got together because they just thought that my uncle was so smart, he had to go to university. And my dad, then 2 years later, they already had the grade 13. So he paved the way, or grade 12 or whatever it was. And got to go to university. Now, he had to work his way through university because the dad was dirt poor. But I grew up knowing that both parents really felt that their university education is what set them up for good jobs. And so we didn't really have much. I don't think any of the three of us thought there was much choice. We didn't think if we went to university, we just thought when we went to university. So yeah, we grew up knowing that education was important, and it was a way out of poverty from my dad's side. And, you know, I guess for my mom, it was a way out of a small farming village. Not that she disliked her town, but I think that's sort of the way I remember it. But they were both very supportive parents too. I mean, I've been very lucky in my life. They were both very supportive.
Yeah, thanks, madam, for sharing your childhood memories with us. I think it will be helpful for us today. So before going to end, so please say something for our student and the new generation researcher.
Well, I wish you all luck for all of you that are trying to go into whatever field. It doesn't have to be physics. It could be math. It could be anything. I just think that if we all do what we're really good at and what we really enjoy doing, I think if you do what you really enjoy doing, you put your heart and soul in it, and then you do your best. And I think that's what the world needs. It doesn't matter what it is. We need so many things in this world that we just all have to be out there trying our best. And so let's do what we like. So we do that. So good luck.
Okay, madam. So thank you. Thanks for giving us this opportunity to attend such an important webinar with you. And it's my honor and privilege to host you in our International Physics webinar. We would like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation. So,
thank you very much for having me.
Bye for today, and bye, madam.
Bye-bye.